That doesn't change anything. I'm still focused.
Caroline, you might not be able to see your own chair.
I can go around.
You sure?
Yeah.
If you want to sit in front too, I'm only going to use these two boards. So don't feel like you have to sit right behind me.
Okay.
I just live streamed my 31B discussion section. It was a success. So I've got audio going directly to the live stream, which is good because I've been losing my voice this week.
We should start a YouTube channel from here.
That's the plan.
I've
I've got 2 other videos up there already. I put another one up this morning. This is going to be my fallback for when my academic career doesn't work out.
What do you want to do?
I want to teach.
I thought so.
That's the goal. So maybe I'll just do that on YouTube. All right, hopefully my computer battery lasts. There's no Also, someone in the chat say yay if you can hear me. I want to make sure the audio is working.
It's already going. Oh wow.
Yeah, we're live now. All right.
How many?
Right now we've got 12 people.
Oh my god, that's popular.
I'm famous. You're in the wings. All right, we're just gonna have to cross our fingers and hope my computer battery lasts. We'll wait a few more minutes to let people log in. For my 31B discussion section, I have it's in CS 76, which is like a Jew. It was very weird.
I heard one of the people who was getting tested for corona, like, was in that classroom, and that's why my chem professor just canceled all of our lectures, but like they were negative.
Oh, no.
We'll get started. Welcome, Internet. Do you know what class you're TAing for next quarter? Yes, I'm TAing for 32B for no white. So I have some of you guys, but the thing I usually tell students is that if you're taking 32B next quarter, and even if I'm not your TA, you can seek me out for help. If we have a completely online quarter, that might be really easy anyway, because I'll be doing this stuff next quarter too. So I'm here to help anyone in 32B next quarter. That's the case.
You
Okay.
for 32.
Probably not, but we'll see. Okay, so my plan for today, like I said in the email, I'm gonna do the discussion here. If you guys have questions in the chat, you can ask, and I'll do my best to just check periodically. Otherwise, we can go. So on Tuesday, if you were in discussion, I did a global extreme value problem, and then I started doing a multiplier problem, but now we've learned no Lagrange multipliers on the final. So today I'm just going to talk about global extreme value type problems. I have great camera. And depending on how much time I have, I might get to do 2 different kinds of examples because there's a couple things I want to say. Also, I apologize in advance. I've been losing my voice this week, so hopefully I don't sound too scary. Hopefully it survives through the next week. All the teaching is taking its toll. Global extreme values. So last week I did a quick example of this kind of problem where the domain was a closed disk. I'm going to do roughly the same thing but with a different shape. So the first thing I'll do is I'll do a similar kind of problem with a triangle. And if you're watching this and you were here on Tuesday, it'll be a slightly different problem as well. So here's the example I want to do. As usual with these problems, I'm going to give us a function of multiple variables. This time it'll be 2xy minus 2y minus x. The prompt is find the global extreme values of this function on some closed domain. Last time, like I said, it was a disk. Today it's going to be some kind of triangle. So here's what I want to do. I want to find the global extreme values on, and here's how I'll describe the domain. The triangle with vertices 0, 0, 2, 0, that's what we're working with today. So, before we get going, let me just sketch a picture of this domain so we have an idea of what kind of closed domain we have. You know, one thing to keep in mind in these global extreme problems is you could be given the information in different ways. Like they could give you some kind of inequality, like x squared plus y squared is less than 1 or something like that. Or they could give you like a region bounded between some lines. Or here I just kind of described in words. It's a triangle with some vertices. So the information could be different. In this case, 0, 0 is right here. 2 zeros maybe over here. And then 1, 1 is probably right. So that's our domain. Also, if you guys online can't see anything I write in any way, you can just yell. All right. What's the general strategy for these problems? Step 1, and so I drew this picture last week. I'm going to keep drawing it because it's really important to me that it captures the idea of everything we're doing here. In the one variable case, so thought bubble within a thought bubble, if I gave us a function on a closed interval and I said find the global extreme values, how do you do that? You look for critical points on the interior. That would get you all these local mins and maxes, the hills and valleys. But that's not quite enough, right? You also have to check that. It works exactly the same functions. So step 1 is going to be search for critical points on the interior. And then step 2, which is usually the more involved part, and that's what we'll spend most of our time on, is checking. All right, but part 1, all we need to do, what's the gradient of this function? The x derivative looks like it'll be 2y minus 1. And the y derivative is going to be 2x minus 2. We're going to get a critical point when both of these things are 0. So critical points occur when both this and both this are 0. Not a difficult system of equations to solve. But one thing to keep in mind, and for those of you guys that were in section on Tuesday, we started doing one of the Lagrange multiplier problems. The algebra can be difficult. That's really the main obstruction in finding critical points. Uh-oh, video skipped. Damn. All right, we'll do our best. Like I said, fortunately, this one's pretty easy to solve. The first equation tells us that y should be a half. And then the second equation tells us that x should be 1. What that means is we've got one critical point, excuse me, on the inside at the point 1. Now, it's always good to check, do we actually care about that critical point? Like, is that critical point actually in the domain? In this case, yes, it is. 1, 1/2. But in these problems, if you found a critical point at like 2,020 gazillion, that is a critical point of the function, but because it's not in the domain that we care about, you don't have to worry about it. Okay. That was, yeah.
Is like all of the real numbers, if I say the domain is R squared, is that a boundable domain?
So it wouldn't be a bounded domain.
So I can say that I have a maximum.
Right. So the question was, if the domain is all of R2, what's the deal there? Because that's not a bounded domain, it's not a closed domain. You could ask the question, like, find global extreme values if there are, but they might not exist. So probably typically what I would expect on a test is you'll get a question with a closed domain so that you can define extreme values.
If it asks for global extrema on an open interval, do you just find critical points? Or like local?
Yeah, you would search for local extreme values, but then pretty much the same situation because the domain. All right, so that was step 1. We found critical points. Step 2, we need to check that. I did, maybe confusingly, I had to squish it in because we were running out of time, but I did some weird like cosine t, sine t parameterization thing, and I checked the whole boundary of this. In a problem like this, we're not going to be able to do things in one fell swoop. In other words, it's not possible to parameterize the entire boundary curve all at once. So this is going to have to be broken up into 3 different problems. Yes, so after this live stream is over, it'll be uploaded to the channel as a regular video. So if you want to rewatch it or whatever. Okay, so we need to do each edge individually. Let me check the bottom edge first. Like I said last week, what I did is I did this weird parameterization thing, which is the thing to do. I'll do something here that might look a little different, but I claim that it's really the same thing, and this is something I can talk about in a bit. But roughly what we want to do is parameterize the bottom edge. In this case, one way we can think about that is I could ask the question, what's the equation of the bottom edge? Yeah, y equals 0. That's what defines the bottom edge. Now, to be a little bit more precise, y equals 0 is the entire x-axis. Don't care about the entire x-axis. What do we actually care about? We just care about this interval. So I have to give you a restriction. And the x values range from, it looks like, 0 to 2. Here's the boundary data for the bottom edge.
So would it ever be a case where it's greater than 0 and less than 2, but not equal to it?
In that case, your domain will be closed. So if you have a closed domain, you should always get like less than or equal to signs. But you could cook up regions where that's not the case. The question there was, are these things always going to look like less than or equal signs? For these kind of problems where you have general closed domains. Yes. Okay, so what does it mean to check on this edge? Well, the function we care about, I think I've erased. But I just need to look at f of x comma 0. That's what it would mean to restrict the function. Okay, so if I remember correctly, the function was 2xy minus 2y minus x. So if I plug in y equals 0 there, 0 minus 0 minus x. That's the function that we have to optimize. Now, what I would usually do is, because this looks kind of awkward, because I've turned this into a one variable function, I'm just going to rename this g of x. And g of x is the thing that we want to optimize. And I think I maybe drew a picture like this last time, but what are we doing? Here's the domain. The domain is a Dorito. The graph of this function is going to be like some floppy Dorito sitting up in three-dimensional space. And when we check along the edge, I'm tracing out the curve on the graph just over this line. And what we're doing is we're finding all the fills and valleys in that curve. So like I said, this is just a one variable optimization problem. We know how to do that. How do we find a hill and a valley of a one variable function? For critical points, take the derivative. But in this case, the derivative of g is negative 1. Negative 1 is never 0, so this boundary roller coaster doesn't have any critical points. And so then we move on, right? Nope. Anytime you optimize a one variable function, you also have to check. So for this edge, there weren't any critical points, but we do have to record 0 and 2. So check n, please. Now, when x equals 0, what y coordinate is it going to get? If I go back here, the restriction here is that y equals 0, so the y coordinate of this point is 0. Okay, so I've picked up a new point. So what I'm going to do is I'm going to record all the points that we care about up in this picture. One of them was this blue critical point that we got from this first step. Here I picked up another point, which is 0, 0, which is the corner of this triangle. X equals 2 is going to give us the one of the other corners of the triangle, because 2, 0 is right there. Okay. That's the body edge of the triangle.
When we, back in step 1, when we find the critical points on the interior, why doesn't it naturally pick up the boundary?
So the question is, when we find critical points on the interior, why don't we pick up the boundaries and do that? Because the derivative might not be zero. For example,
okay.
just in the one variable case, if I had a function like that, at the boundary, the derivative definitely isn't zero. That's exactly why we have to check. Good. All right, so one edge down, 2 more to go. These problems are long and there's no great way. So I guess I'll keep this picture. I don't want to erase that. So let's move on to this edge. And I'll ask the same question I did before. What is the equation of this edge? Yeah, it'll be y equals x, but this will be something that you'll have to figure out for yourself. I've got the point 0, 0, 1, 1. Y equals x. Again, strictly speaking, y equals x is the entire line. I don't care about the entire line. I only care about this segment, so I need to impose a restriction. For example, I could say that x values are restricted between 0. So if it were me, I would say left edge. The equation there is y equals x, and the restriction is x only ranges between 0. So what function do I get when I impose the restriction y equals x? I'm looking at f of x comma y. And you'll have to help me out again because I erased the function. It was 2xy. So that turns into 2xx, which is 2x. Minus 2y is x. Minus x. So it looks like we get 2x squared minus 3x. This is what I'll call g of x again, to represent the boundary function. Just like before, we got an optimization problem of closed interval. What do we do? On critical points, the derivative of this g is 4x minus 3. So in this case, we do get a critical point. It looks like when x is 3/4, the derivative of g is 0. So this yields the point 3/4, comma. What is the y coordinate? The assumption that led us here is that y equals x. So if x is 3/4, so is y. So the y coordinate of this point right here is 3/4. And that's a new point to check. And I'll ask the same question I did is, hold on, do we actually care about that? In this case, we do, because 3/4 is between 0. So 3/4, 3/4 is a yes. It looks like that's right here. done with this edge? Strictly speaking, no. We have to check the endpoints. One of the endpoints is going to be down here, which we've already accounted for. But then I also get this endpoint. That corresponds to x again. So maybe for now I'll just say accounting for edge. We also need to
When you know that works.
say that again.
Like, why in the first part do we check the endpoints like x equals 0 and x equals 2?
And then I didn't do it here. I probably should. So maybe let me do that. If I mimicked what I did down here, one of the endpoints is 0, is x equals 0. What's the corresponding y? 0. So I get the point 0, 0. But I already accounted for that. So roughly what's happening is anytime you have corners, you have to check all the corners. So if you want, you could do that. That would make me pretty happy. You could explicitly check everything, but probably you're fine just saying, like, I know I need to check all the corners as long as I account for them. Okay? Yes, so I think the question is, do we always end up testing the vertices for a domain? And yeah, I guess I kind of answered that before I get the question. Anytime you have corners in your domain, you're going to check them because you're going to realize those corners as endpoints of your boundary. So I think as long as you account for them, you can write it up. All right, one more edge, more of the same. Same question as before. What's the equation of this last edge? Think a little harder. It should be y equals 2 minus x. So now we're pros at this, impose that restriction on the function, and we get a new boundary condition to check. So C is the right edge. The right edge is given by the equation y equals 2 minus x. But again, the line y equals 2 minus x is the whole line. Don't care about the whole line. I only care about the segment. What is my parameter restriction here? X values are going to range from 1 to 2 in this case. So these will be the endpoints. 1 to 2. All right, so as before, I want to look at f of x comma y is 2 minus x. This is really testing my memory. It looks like it's 2xy is quantity 2 minus x minus 2y minus x. That's the function we need to check. If I simplify this a little bit, let me know if I screw up. Oh, let's see, I get a 2x plus 4x minus x is 5x. I get a minus 4. And then the squared term is minus 2x. Check it out. Next. All right, I'll call this G. See what we've been doing. G prime of x here is negative 4x plus 5. Which means there's a critical point at 5/4. Same question as before. Do we actually care about that point? Yes, because 5/4 is between the two. So that checks out. What's the corresponding y value? Uh-oh, now I've got to do algebra. 2 minus 5/4 is, did I screw it up?
I got 3x, but I don't know if it's just like a me being.
No, I very well could have screwed up. Here's a 4x.
4x.
Oh, yeah, 4x plus 4x.
Wouldn't that be plus 7x? 8x or 8 minus 1 is 7.
Oh, I'm losing my mind. I think I did. I think I did it right first. 4x plus 2x is 6x
Oh,
minus
good
x.
job, Jordan. Yeah.
This stuff's fine. Multivariable calculus I can do. Middle school algebra. That's okay. 5/4, what's the y value? 2 minus 5/4 is 8 minus 5 over 4, which is 3/4. So that came from 2 minus 5/4. And again, we do actually care about that point because 5/4 is between 2. So that's probably right. Okay, my picture is turning into a mess. Oh, and maybe I should say something about the endpoints. As always, we have to check the endpoints, but we've already accounted for both of them because those are these two numbers. But I'll still say that we've accounted for endpoints. We have accounted for endpoints already. Now, what's the point? We did all this stuff and we generated a bunch of points. To find the global extreme values, at this point it's as straightforward as just plug all of them into the function. Whichever one is the biggest, that's the global max. Whichever one is the smallest, that's the global min. Done.
What if you get like the same answer? Like, say your biggest number, like you had 2 of them.
Okay, so the question is, what if we do that? Like, let's say I found 2 points, and I plug them both in, and they're both 5. What's the deal? My answer to that would be, if you were doing this problem on a closed domain, like on a bounded closed domain, then we know, and this, it sounds like this was the main idea communicated from Monday's lecture, is that if you're doing this optimization problem on a closed domain, you will always have a max and you will always have a min. So if you plug in your 2 points and one of them's 5 and the other one's 5, and it's genuinely on a closed domain, that would mean that the function that you started with was 5. Because that would mean that the min and the max is both 5 and therefore it's 5. The real answer is probably if that happened, you may have made a mistake. Yeah, it's a good question. Questions? Nice. Okay, so lastly, we just have to plug in all these points. I did this on Tuesday. I might skip that part.
That's fine.
That's fine. Okay, so let me say that the last step plug in all the blue points. F. The biggest is the global max. Smallest is the in theory that would finish up. So that's a pretty standard global extremization problem where you have some weird shaped boundary. You look for critical points on the inside, which we found one of which. Then we have to check all along the boundary, making sure we account for corners, which is to say we account for the boundary. Any in-person questions about that one? Any chat questions about that one? What would we do for domains that are circles or ellipses? That's what I had planned next. So, because we don't have to talk about Lagrange multipliers today, really all we have to talk about is global extremization. So I just wanted to give you one more example of maybe some details of what could happen. And like I said, for people that were in discussion last week, I did a circle example, but I did it pretty quickly. And I want to go through a different one to maybe explain the thought process and show you actually two different things at the risk of being confusing. So, also at the risk of being confusing, to give you what is now irrelevant comment, because we don't have to worry about Lagrange multipliers. In general, to check the boundary, you could turn that into a Lagrange multiplier problem. So if that makes sense to you, you can think about that for fun. If not,
Post the session for Lagrange?
I might. So the question was, can I post a video about Lagrange multipliers or something? I might actually do that just because it's a little sad that we're not covering it in class, because of all the things that you learn in 32A, probably the most useful thing is Lagrange multipliers. My roommate is a statistics PhD student, and I mentioned this to him last night, and he was like, "Oh my God, like I use Lagrange multipliers every day. Like, it's the only thing I use." So the one thing that you might actually really use in so I might as well. Anyway, until then, here's another example. We can start it, and then we can do what we feel like. Same thing as before. Let's do the function xy squared on the domain. Let f be that function. And what I want to do, I want to find the global extrema. On the domain, which is all the points x squared plus y squared, which are less than 1. So here the domain information is given a little bit different. And you just have to be able to figure out what's happening. Otherwise, it's roughly the same kind of problem as before. If I draw a picture of the domain, usually when you're given information like, oh, some stuff is less than or equal to some other stuff, the way to think about the shape of the domain is to consider the equality case, which in this case is x squared plus y squared equals 1. And I think, that's a unit circle. all of the points x squared plus y squared that are less than or equal to 1. That's everything. All right, so there's our closed domain.
Do you know it's closed just because it's less than or equal to?
Roughly, yeah. So the question is, do I know that it's closed because there's a less than or equal to sign here? The answer is pretty much yes. Generally speaking, closed domains are going to have less than or equal to signs because a closed thing includes its boundary. If I had written this, that would be an open domain. It would just be the unit disk where we don't actually include.
It was greater than or equal to is not closed.
Yeah, so the question was, what if this was a greater than sign? It's closed, but it's not bounded. So it's closed because it still includes its boundary, but it's not bounded. Yeah, it would be like the region out here. And so the question is, would there necessarily be a limit or max?
If it's not bounded.
If it's not bounded, there may not be a limit or max. That's correct. So let's do the same thing that we did first. The gradient of f here is a little easier to compute, or a little easier. Y squared 2xy. In order for this to be 0, y needs to be 0. So critical points in there. Y equals 0. Oh, dang it. That's what I get for coming. Actually, let me talk about this. That's okay. We'll do it. Where do we have critical points?
Isn't it basically along the line where it equals?
Yes. So the reason why I hesitated and I almost changed the problem is that we don't get an isolated critical point. So let me re-say what I was rushing to earlier. In order for this to be 0, this component needs to be 0. So therefore y has to be 0. Then if y is 0, this is always 0. And it doesn't matter what x is. That kind of sucks, but that's okay. What that tells us is that any point of the form x comma 0 is a critical point. So any point x comma 0 is a critical point. Which means we have a whole infinite lines worth of points. That could happen. It's maybe not ideal, but it can certainly happen. Last week you had some homework problems like this, where, for example, you had that one problem that it was like e to the negative x squared plus y squared, and there's like something out front. And roughly that was just like a radial hump that kind of went out like that. And you had a whole ring of critical points. So that's kind of what's happening here. So the question is the domain x is greater than or equal to 0, closed but not bounded? I would say yes. That's correct. Okay, so we have a whole line's worth of critical points. What I really wanted to do with this problem is show you two different ways to check the boundary. Because one thing that I don't think was maybe clear from last week or even today is like when you check the boundary, it's not like there's one thing to do. Good thing about math is you can do whatever you want as long as it's correct. But in terms of checking boundaries, the way it looks could be different. And And roughly, it's just because there are different ways to parameterize the same curve. That's what this boils down to. Anyway, what am I rambling about? Let me mimic what I was doing in the previous problem first. So boundary method 1. In the previous problem, what was I asking? I would look at the boundary, which in our case is this whole circle. And my question was what? What's the equation of that circle? X squared plus y squared equals what? So boundary circle and what were we doing before? We were just imposing this restriction on the function. Now, you have to be a little careful here. It's not as easy as just plugging in, like, oh, y equals this, or x equals this, or something. Here's what I would do. Go up to the function here. I've got a y squared. What if I just solve for y squared? I know that on the boundary, y squared has to be 1 minus x squared. This is the restriction that I can impose on this boundary function. So then I could say, and I'll write it this way, which might seem ridiculous. You can probably write it. F restricted to the boundary. That's what I'm going to call g of x as usual. And what is this? It's x times y squared. What is y squared? On the boundary, it has to be 1 minus x squared. And that's the boundary function that we can check. Also, just so you guys and people online watching know, unless someone comes in this room afterwards, which shouldn't happen, I don't have to stop at 50 after. I'll keep going until we finish this. How's that so far? Okay. Next one. Now, yes, Steve.
Is that squared? The argument x, 1 minus x squared.
Yeah.
Oh, are you asking?
Yeah.
Should I put squared here? So the question is, should I have written a square? No, and this is what's a little sneaky about what I'm doing. But this whole expression here is
Y squared. Okay.
is y squared.
There we go.
Now, same question as before. Do I actually care about this function for all x? No. The x values are restricted. What is the restriction of x values? From here to here. So there's an x restriction for this boundary function. There will always be a restriction when we check this boundary stuff. It's naturally going to happen. So I only care about this for x between 1 and now we've got our boundary problem to optimize, do exactly what we were doing before. Find critical points. G prime of x is going to be 1 minus 3x squared. Oh, which tells us critical points are going to occur when this is 0, which is at plus and minus 1 over root 3. Oh, how's my battery doing? Yeah, we're good. Okay, so the next question, which is the same as before, I've asked the same questions about 30 times today. We have two x values. What points? I get 4 different points. If x is 1 over root 3, what could y be? On the boundary, y squared has to be 1 minus x squared. So this would say that y squared has to be 1 minus this squared, which is 2 thirds. If y squared is 2/3, y could either be plus or minus square root of this. So on the one hand, I'll get a point which is the square root of 2. But then I also have to consider the points negative square root of 2. You know, that maybe is confusing, but what's happening on the picture? What's happening on the picture is that if I just pick the point x equals 1 over square root of 3, on the circle there's 2 values. They're probably not. Likewise, x could be negative 1 over root 3. So we always also, get the points. Negative 1 over root 3 plus square root of 2 over 3. And then negative 1 over root 3, negative square root of 2 over 3. And those are just the 2 points on the circle with x value. Same question as before. Are we done with the boundary? Technically, no. There are endpoints to check. But in this case, we have actually already accounted for those endpoints. Because the endpoints would be when x is negative 1 and when x is 1. What are the corresponding y values? Y would be 1 minus 1, so y would be 0. But we've already accounted for, because we started out with this whole line y equals 0, we already accounted for this. But if we hadn't, we would have to additionally.
When we made the function for the boundary, if you were to graph that function, g of x, does that trace out a circle?
No. So Shai's question was if we were to graph this boundary function, would it trace out a circle? What it's tracing out there is, maybe I can try to describe it. So the function x minus x cubed, what does that look like? So where it looks like that. And I'm restricting it to just being negative 1 to 1. So there's a picture that you guys. So what is this thing in the context of like what we're doing? If we look at the domain, like I was talking about before, the graph of the function on this domain would be like picking up the disk. So it's like a floppy pancake, and then the surface is going to be something sitting on this. that function right here is what happens if I start over here and then I want to travel along the surface of the function. Sorry. If I want to travel along the boundary of the surface, it's going to go up and then down at 0, and then p to the 4, and then back to 0. So what you should not make any sense, but what you should visualize when you think about these boundary functions is that this function is on top of this. So here, like I'm going up, and so then this picture makes sense because I have a hill here and a valley here. That corresponds exactly to this point and this point. I go up, there's a hill, I go down, and then there's a valley, and I go up, likewise with the valley.
Could I call that a vertical trace?
So the question was, could we call this a vertical trace? I would say no, but it's a good question. I would say no because I think when we talk about something like vertical traces, actually I'm glad you asked that. When we talk about something like a vertical trace, that's specifically chopping with a plane. So I've got this surface sitting out here, and I would call a vertical trace anything where I chop with a plane. One way to think about what that picture is instead of chopping with a plane, I'm chopping with like a cookie cutter, like a cylinder cookie cutter. I'm going like that. And the picture that you get on that cylinder is that. So it's a trace in some sense. I don't know if I would call it a vertical trace, but it's like a cylindrical trace or something. Yeah, question.
And why does that account for both the top half of the circle and the bottom?
That's another good question. Because I left it as y squared.
Okay.
So if you think about if you had solved for y, when you take a square root, what do you have to do? You have to account for the top and the bottom. By leaving it as y squared, you can keep that. Okay. Anyway, let me just do one more thing and then we can stop there. I wanted to show you a different way to check it out. More similar to what I did last week.
Sure, that could you once again explain why we don't take the endpoints at y is equal to?
Why we don't?
Yeah.
So we do, and maybe I should probably write that up here. Maybe we say boundary points x equals plus and minus 1. We do take them into account, but what I was saying is that we've actually already taken them into account when we found critical points. Because we found that any point on the x-axis is a critical point, which means those boundary points, x equals net 1 and -1, we already accounted for them.
Wait, are we gonna keep going with this or are we doing something? Because I have a question about like the end of this.
Okay, so what I was going to do the same problem, but I was going to get these 4 points in slightly different.
Okay.
But from here, what would you do? It would be just the same as before. You've got these 4 points, boom, 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 boom. And then you've got this whole line's worth of points. You would, okay,
That's my question.
you would plug in all of those points, whichever one's the biggest, you win, whichever one's the smallest, you win something. And okay, so what I shouldn't brush over is, Joe, how am I supposed to check 10 million gazillion infinity points? The idea is that any point here is y equals 0. What's the value of the function for any point y equals 0? F was xy squared. But no, that's a good question, and this is what you have to say. You have to say that for every point on this line, f.
Are there any situations where you get a line, but
I didn't let you finish your question.
no,
Maybe
yeah.
for the internet, the question probably was, and you can correct me if I'm wrong, could I get a situation where I have like a line's worth of critical points, but that the function is different. No, because it wouldn't have been a critical point. If you want a 32a answer, if you had a line where the function changed on that line, then you could take a directional derivative along the line and you get something like 0. But then that would imply so that would happen.
So when we say that that y is equal to 0 is a critical set of points, so does it mean that if this is x is equal to 0, coming here it's going like this? So what? And that along this we want to see how it's moving.
So roughly the fact that this is just a line's worth of critical points means there's some kind of like half pipe behavior going on. Like if you think about z equals x squared or something, it's like an infinitely long half pipe. All right, so really quickly,
Thank you.
Obviously, let me just really quickly show you a completely different way to check it, which mimics what I did last week. So boundary method 2. And I might not do this to completion just because I'm tired. And I need at least a 15-minute break before office hours. But think about what I did last week in section. The boundary curve is a circle. How did I check the boundary last week? I parameterized the circle with cosine t and sine t. So alternatively, here's what we could do. We could say that the boundary is described by x equals cosine t, y equals sine t. These are parametric equations that trace out the boundary circle. Now, anytime you have a parameterization or anytime you have parametric equations, you need to specify a domain for your parameter. So we can do whatever we want, but in particular, if I send t from like 0 to pi, I'll trace out the boundary. Okay, so I have a parametric description of the boundary, but how do I use this to check the function of the boundary? These are the restrictions I impose on f. F of xy is just going to look like f of cosine t sine t. So the g function that I have is now going to be a function of t, and it'll be f of x, y. Which, here's f, it would be cosine t times sine squared. That's the function that we would optimize as well. How do you find maxes and mins of a one-variable function? Same thing we've been doing, take a derivative. Now, I suspect that this is probably more difficult than what we did in the first method. Maybe not. Let's see. If we take a derivative here, I'll get negative sine cubed t and then plus 2 cosine squared t sine t. And then we have to figure out where this thing is 0. So we have some trigonometric equations to solve. I would factor. I noticed that I can factor out a sine t. So factor out a sine of t there, and you'll get 0 equals sine of t times negative sine squared t plus 2 cosine squared t. There are two possibilities. Either this is 0 or this is 0. If sine of t is 0, this happens when t equals 0 and 2 pi, which is going to record the point here, which we've accounted for, and here, which is the same. Oh, also pi. I forgot about pi. Sine of pi is also 0, so that would be this point, which we accounted for. Then the harder part that I might not be able to do on the fly. What if this quantity is 0? So I don't know how you guys would approach this, and like I say, I think I prefer the first method for sort of this reason. But how would you go about solving an equation like this?
Like calculate what the tangent is. Like take sine to one side and divide it.
Oh, okay, that's a good idea. So Abhishek suggested we could divide through by say cosine t, cosine squared, as long as cosine is not 0. So you have to account for that separately, and so I think you'd get some extra points here. Which you could still do. You'd introduce some extra points, but yeah, that's a good idea. You could write this in terms of tangent.
I don't know the idea what tangent is.
I was going to give my idea. I'm curious.
Mine was in the beginning when we wrote it as cosine t sine squared t. I replaced it with 1 minus cosine squared. I replaced sine squared with 1 minus.
Oh yeah. So that's ultimately what I would do here. It's probably another way that you could solve an equation like this is to write it entirely in terms of sine and cosine. For example, cosine of t we could write as 1 minus sine squared. And so this turns into 0 equals 2. So negative 2 sine squared minus sine squared is negative 3 sine squared. This is pretty cute, actually. All right, I'll finish this off just for fun. Solve for sine of t. And what do you get? If you can see, sorry. Sine of t is the plus or minus square root of 2. Let's think about this for a second. So then I look at that and I think, oh shit, what is t? I know a few unit circle values, but that maybe doesn't look like any unit circle thing I know. Like I know root 2 over 2 or like 3 over 2. So I'm screwed. What do I do? The answer is I don't actually care what t is. What do we ultimately care about? We care about the x, y, 2 y values that we care about, which if you remember, I've erased the 4 points that we had earlier. Those were exactly the 2 y values that we had. So there are the 2 y values, and using that you can generate the 2 x values, and you'll get the exact same points. Anyway, I just wanted to do that to give you guys an example, to maybe spend some more time. Last week I had to rush this trig parameterization thing. Here's an example where you kind of have 2 different functions for checking. You could do a kind of trig parameterization, or the first thing I did is a parameterization not involving trig functions, and I parameterize using this. And so a lot of times there's multiple ways you can do this kind of thing. If you get a circle as a boundary or an ellipse as a boundary, it's probably going to be one of these two things. You either want to use trig functions to parameterize or just use the equations. Okay, I'm going to call it there for today. For everyone listening right now, I'll be doing exactly this with review sessions next week. I'll plan on just live streaming them, and then we'll get to covering material. And we'll probably look exactly what's happening here. So, goodbye for now.
Joe, we need to work on your outro.
Yeah. Also, if anyone has I'm in the market for a better channel name or like a logo or something. Or if you want to be my brand manager, I'm hiring. So.
You just say like, comment, subscribe.
Oh yeah.
You really
Smash that subscribe button. And like I said, this video will go up on the channel as a regular video, so if you want to rewatch things, it'll be up there.
I got it. Not your average Joe.
Ooh,
Not your average.
Steve says,
Joe.
not your average
That's
Joe.
pretty good.
That's pretty
Average is like a math. Oh,
Yeah.
good.
wow.
Ooh.
Guys, this is
That's
Covell's
pretty
last
good.
meal before they close.
Oh, really? I'm not going.
Oh, dang.
No, tomorrow lunch.
Whoopsie.
Joe
Too
the
bad.
math bro. That's a good suggestion.
No.
No, I kind of like that.
Joe math.
Joe the math bro.
Wait, so
Oh.
for your thing online next week, is there an option if we want to come in person, or just
I'm not going to stop you if you want to come in person. Officially, I'm supposed to tell you don't come in person, but I'm going to show up to the room and I'll talk about math.
Hours?
Same, yep, same deal with office hours. Officially, you are not supposed to come, but maybe I should be saying this on the record.
Are you gonna be like in your physical office?
Yeah, I'm just also going to try to Zoom. Yeah, I'll be on this. Same time as usual, 3. I think, right? Yeah. All right, see you guys.
Joe, I was in the LA Times.
You were?
Yeah,